My name is Anish. I work at Trifacta, which I'll explain a little bit more about what they do. But what I'm going to be talking about today is something called programming by example, which, and it's a little bit specific to Trifacta in the sense that I'll be going over the story of how we integrated it with our application. But it's a methodology that can be applied to a lot of different data applications and might be a new way for users to actually interact with data. So hopefully everyone can get something out of it. All right, so quick overview. So I'll just first explain what programming by example is. I use the acronym PBE, so that's the one acronym you might have to remember. I'll talk about algorithms to kind of solve it because it is this theoretical problem, and there's actually like 10 years of research on this, so it's pretty exciting from that domain. I'll talk a little bit about there you go. I'll talk about like integrating it. So all the challenges that come from integrating something that's like this theoretical algorithm into a data application that end users, non-technical users, need to be able to understand and use. And then finally, I'll talk about how we make it something of an ML-driven feature and like how we integrate analytics into the feature itself. Because one of the values that we have at Trifacta is start with the user, and the user's interaction with our application drives a lot of our product in other ways. So it should be the same for this feature. Okay. There we go. I just had to point it. So a little bit about what Trifacta is. We are a data preparation platform. A lot of you guys might have heard this quote that data scientists spend like 80% of their time cleaning their data and only 20% of the time actually doing data science. And whether or not that's true in any one specific case, there's a lot of value in making the data cleaning and data wrangling part much smoother and much easier for users to deal with. So the way it works is that Trifacta kind of sits between a lot of like different import sources. So you can see at the bottom, there's like icons for files. We support reading from databases. We support a lot of cloud vendors as well. And all of that data we import into Trifacta. Users then clean their data. They can wrangle their data, and it's all done in a standardized format. And then finally, whenever they're ready to go do visualization, go do analytics on it, we publish their data to the source that they want us to. So for example, we can publish to Tableau if they want to do visualizations. We can publish to DataRobot if they want to do some automatic machine learning. And so sitting in the center gives us a lot of flexibility because we can connect to a lot of import sources and export sources. So how do users actually clean their data when they're in Trifacta? We have this page that we call Transformer, and it's very similar to Excel in some ways. I'd like to describe it like that for people who aren't familiar with like data products. But as you can see, it's like a tabular format. We have a lot of nice like visualizations at the top. These are meant to kind of guide the process of, if you have like missing values in a certain field, what the formats of different columns look like. These are all things that help with the data cleaning process. The way that users kind of interact with this data is primarily through a script-like interface. So all you guys have done SQL, I'm sure, or at least familiar with it. It's similar to SQL. It's a DSL, a domain-specific language that's built for Trifacta, but a lot of the operations we support are things like maps and mathematical operations, aggregations, a lot of the similar stuff to actually what John Ferguson talked about in the first talk. And yeah, and that's like been so far the primary way that people interact with data. You define an operation, you run it, and then you get the results in this view. One thing I will point out is that this is a sample of data. So this application actually runs as a web app. And because we're limited by like Chrome's memory requirements, we can't load your several gigabyte table into memory in Chrome. What we can do is load like a sample of 5 to 10 megabytes. And whenever you're comfortable editing that sample and whenever you've gained confidence in what you've done with your data, you can then run this script as a job on the rest of your data. And another thing to point out is that we don't touch the original data at all. It's all copied, and so you don't have to worry about like data permanence or anything like that. So data cleaning. This is like a term that means a lot of things, but one of the challenge I'm going to talk about today is this challenge of standardization, which has like a million different meanings. But in this case, what I'm talking about is standardizing a column that has like a lot of differently formatted things into a single format. So in the example given, it's unfortunately a little hard to see, but there's a date column with things in different DDYY formats. And suppose that what you'd like your data to look like is to have this date column be in one single format. So right now, before we looked into this thing called programming by example, we had a little bit of like pre-existing standardization functionality, but it was very specific. It involved a lot of custom code, and it ended up being sort of brittle and sort of specific to dates. So this is kind of an example of what a user would like to do. And right now in our product, it's like a very limited use case. Our challenge was to kind of generalize this. Yeah. So to drill down a little bit further, let's say you have a column of phone numbers, and they all have very funky formats. And you'd like to make them look the same and add an international code to the beginning. This doesn't sound like a very hard problem, but in practice, it can actually be pretty confusing. There's a lot of edge cases that you have to handle, and there's a lot of like funky regex stuff that you have to do for this like one simple standardization task. And so I went on Stack Overflow to try to figure out how you would do this in SQL, and this was the third answer down. And what's funny about Stack Overflow is like the first answer is usually like a really short, pithy thing, and then like every answer below is like, wait, no, that doesn't work. So everyone's like finding problems with it. And it turns out there's a lot of like edge cases that this kind of script has to handle. So if a user wants to do something like this in Trifacta or in any data application, they often have to write this like long script out themselves, which might be okay for technical users, but for non-technical users, it's definitely a problem. It means that they would have to find a technical user to be able to do this, and that is a lot of overhead, as you can imagine. So what if instead of writing that script, you simply type out what you want your phone number to look like, and then have everything happen immediately? That would be pretty awesome, right? If you could just type out +1 949 727 6490 with the spaces and have the rest of your column be like immediately formatted. So that's what programming by example kind of is. So in PBE, rather than specifying your program, so like your SQL script or in Trifacta our language, rather than specifying that directly, you specify these things called input-output examples, where for any given record of your input data, you type out exactly what you want the output for that example to look like, and then the machine actually figures out the program that you're trying to do and automatically applies it. So this is like, it's sort of a declarative way of interacting with data. And there's tons of research on this. And so what we tried to do at Trifacta was implement it, because we had been getting a lot of like feedback from users that, hey, I just want phone numbers to look like this. What's the series of transformations I need to do it? And it would lead to a lot of like headache and pain, whereas if they're able to just type out exactly what they know they want the output to look like, it's much easier. So yeah, so I'll talk a little bit about the algorithm, because some very cool parts of it. And the algorithm here is basically given a set of input-output examples, what's the program in some domain-specific language, be it SQL, be it R, even be it whatever, that would take you from those inputs to those outputs. So the way that most PBE algorithms work is in 2 steps. The first step is to synthesize a set of programs that could theoretically represent that input-output example. And then usually, you end up synthesizing quite a few programs, but let's go through an example. So let's say that you have Harry and Hermione over here, and you're trying to get their initials. So pretty simple task. And as you can see, there's 2 input-output examples that, let's say, the user has specified. You can also imagine cases, by the way, these are single-cell inputs and single-cell outputs, but you can generalize this whole idea to multiple column inputs and multi-column outputs as well. But let's say they've provided these. So the first step is, let's figure out all the programs that could possibly go from Harry Potter to HP, Hermione Granger to HG. So the 3 programs that listed, because people are very far, So one of them is concatenating the first character of the first word with the first character of the second word. If you imagine that we have some kind of language that supports like string concatenation and character lookups, this seems like a pretty simple program and would probably be the correct one. But then there's other ones that also do the same thing, right? So the second one is concatenate the string literal H with the first character of the second word. In the example given, both of their names start with H, so it would suggest that as a valid program. And then finally, an even more ridiculous one, if the word is Harry, then H, P, otherwise HG. So these are all three potential programs that the synthesis step could recommend because these all are theoretically consistent with the examples provided. But as you can see, the second and third ones are pretty terrible, and they wouldn't generalize well to like any other name. So that's where ranking comes in. Please. OK. So the idea behind ranking is you simply use some kind of metric, and we'll talk about a little bit of the heuristics and ML that can go into that process. But you're basically trying to pick the program that's most likely to be what the user intended, and also most likely to generalize to the rest of their data. So in this case, obviously, like the best program is simply to take the first characters of each words and concatenate them. So these are kind of the two modules of most PBE algorithms that have kind of come about. But there's a big problem with synthesis. So generating all the programs that are consistent with a set of input-output examples is not only like, the DSL could be not only so vast that it's impossible to even like go through all of them, but in a lot of cases it's like straight up unbounded. You know, there's a lot of reasons why that might be. You might have like a large function catalog. At Trifacta, we support like 200 functions and SQL, and a lot of these languages support a very, very large amount of functions. If you're trying to just like brute force search like every possible program you can come up with up to a certain depth, and then just check if it works with input-output examples, your user is going to be waiting for centuries, right? You're like looking through way, way too much stuff. And there's things like nesting. You might be suggesting programs that are multiple steps. Numeric and string parameters can be like whatever. How do you search over those? And there's a lot of like optimization tricks you can use here. You don't have to do a brute force search. But even so, it becomes very, very unperformant to try to just synthesize everything. So the way that most kind of PBE algorithms get around this is with the observation that when people are using this tool, it's usually because they're trying to format strings. And that's like been the biggest use case so far, and that's something that is a little restrictive in some senses, but in a lot of senses it makes things much easier because the domain-specific language for dealing with strings can become very specific to like things like formatting. So you have things like concatenation, uppercasing, lowercasing, substrings, regular expression matches, and those kinds of things you can optimize very heavily over and then like come up with an algorithm that's very, very good at synthesizing programs for those. So this is definitely what like pretty much every algorithm in the last like 10 years has kind of gone through. And so at Trifacta, we sort of initially like started out with this method of just like, okay, let's try to just write a better string format by example. But you know, down the road, it's definitely something that we're trying to look at as to how can we extend this DSL to be what our Trifacta DSL is, which is a much, much bigger set of operations of math, schema, aggregates. But yeah, so assuming we're starting from a string formatting DSL then. Okay, yeah. So few algorithms real quick. The first one that you guys might have heard of that's in Excel 2013 is flash fill. This was kind of like the first real implementation of programming by example. It was, oops, gotta go previous. The guy who wrote this, Sumit Gulwani, is considered by many to be basically like the inventor of programming by example. He works at Microsoft, and his research basically enabled this feature to happen. The way it works is that it's it takes input-output examples, and it supports a string DSL that has a bunch of formatting operations, ternaries, and loops. and it's pretty good. You can try it out in Microsoft Excel if you want. It's available for free. It's available in a lot of other Microsoft products as well, Power BI, PowerShell, Power Query, I think. And this was kind of a good first stepping stone for a lot of applications. But one thing that kind of happened a few years later was that people realized that, well, if you're just learning on the examples that users have provided, then you're oftentimes going to be very sadly mistaken as to what the user is actually trying to do. The reason is that input data can be very vast and very heterogeneous, right? You might have a user providing examples for, let's say, a certain format of phone numbers, but the rest of their column might be filled with a completely different format of phone numbers. And if you only learn a program based on the examples they give you, then you're necessarily going to be missing out on a lot of the additional context about what they're trying to do just because they didn't put in the right examples. So the way that Blinkfill, which was an algorithm in 2016, came about this is, well, let's do some kind of search over the input data, the entire input column, come up with some kind of representation of the different regular expression patterns that could be in that data, and some of the logical patterns is what they describe it as, and then use that as a data structure and inject it into the synthesis algorithm to basically inform what the generated programs can be that are also valid for the entire column. So this also has the benefit of very dramatically reducing the size of the DSL and being much, much faster than FlashFill. So if you play with FlashFill in Excel, I think on average it takes 0.1 seconds to generate a column of data or to generate a program from an example. But with Blinkfill, you could end up with something like 0.003 seconds when we tested it. So we went down this road and we tried to implement it. There wasn't an open source implementation available, unfortunately, but we just did it in Python, and it turned out to be pretty nice. And then yeah, so that those were two algorithms that have proven to be pretty good on a set of real world Excel string formatting tasks. But one thing that we have been struggling with is the ranking step. So just to quickly talk about a few of the ranking strategies that some of these algorithms used. The very simplest thing you could do is what they'll reference Occam's razor, which is basically the idea that users trying to do the simplest program possible, right? So these are two examples in Trifacta's DSL. They're both doing the same thing. You're taking the substring of a column from indices 0 to 2, but clearly the first one is just doing unnecessary stuff. You don't need to be taking the substring and merging them. Just take the substring and specify the indices correctly. And this is kind of a contrived example, but it's pretty much the only heuristic that you really, really need. But you can go more in depth with this, right? So there's a lot of other heuristics you can use when you're actually ranking them. And basically, the way that it would work would be that the ranking algorithm would choose a program that satisfies the most of these heuristics. So you can prefer a certain function catalog. You can note that when you're trying to extract text, for example, your user probably wants to extract them between two delimiters. So prefer programs that are doing that as opposed to other crazy regex manipulation stuff. A very obvious one is to use metadata about the column to inform what kind of functions should be available or not. So these are great, and Blinkfill does a lot of them, but they're still kind of brittle. And one of the questions is, can we, rather than custom writing a bunch of ranking methods and heuristics that end up being just a bunch of if statements, can we improve them by looking at user data? And so an architecture that you could imagine is something like this, where once you've synthesized your set of valid programs, and let's say in Blinkfill's case, you're synthesizing a much smaller set because you're informed by data from the column as well, you extract features from each program and basically create a feature vector for each program that maybe encodes some of these heuristics as values. And then you basically have a model that predicts off of each vector what the likelihood that it is the correct program is. And using that, you get a highest ranked program that's informed a little bit more by user data, because you can train these models to basically say, what's the likelihood that given this set of like heuristics of a program that it is a correct one. And there's a lot of like ranking algorithms out there. There's a lot of ranking models out there. So the ones that we commonly use at Trifacta are logistic regression, but we're starting to look at some more sophisticated ones. And CRFs are kind of interesting because CRFs or HMMs, any kind of graphical model that represents the dependencies of our features would be nice. But this kind of approach is something that might be good because it allows you to custom tune a lot of heuristics, but it leaves the actual prediction step up to a model that's hypothetically trained on user data. So that's pretty awesome. But there are some challenges here. So first is, well, the training data itself is something that should actually be pretty easy to generate. If you're in a data product where people are doing transformations on data, what you can simply do is take a look at the data before a transformation is applied, take a look at the data after it's applied, and then have those be input-output examples. And the transformation that actually was applied is the correct label for whatever model you're choosing. And in theory, if people are doing operations on your product, that's where you want to get training data from, because that's going to be better than any kind of large data set. It's going to be personalized to what people are actually doing in your product. And so that was kind of one of the things that we set up at Trifacta, was a feed of people's like interactions and a record of input-output examples that come from them. However, that is definitely not great if you're trying to not save like personal information. So this SSN credit card numbers, email addresses, they show up in data that comes in Trifacta all the time. And we can't save those in our analytics pipeline because we'd be like, breaking a lot of laws. But what we can do is this idea that, okay, we don't really care about what the specific values of some of these fields are. We just care about, like, from a string sense, what is the logical format of them? So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, let's say that's your social security number. You don't really need to know that those are the exact digits when you're trying to learn that transformation. All you need to know is where the digits are and where the delimiters are. And so this kind of masking has helped us a lot because we're able to kind of save data that's based on format and not actual user data. And from the model's point of view, hopefully because we still have access to what the pattern transformation is doing, we're not actually like losing any information here. So this is like one strategy that is sort of helping us right now. But in theory, we'd also want to have some kind of online trained model that can train directly on users' data in their browser, but that is not sending any data back to us. So making that guarantee is definitely an open question. Yeah, so that brings us to some like really cool stuff now, because over the last 10 years, there's been a lot of work at neural programming, by example. So the idea is, rather than doing synthesis, rather than doing this ranking, what if we can simply generate a program step by step, given some encoding of input-output examples? And this avoids a lot of the headache of like restricting your DSL potentially, and can, given the results of generative models on a lot of text, it seems like it's a pretty cool approach. There's a lot of things you can mean by outputting program here, right? So, you could be classifying from a list of programs. So this could run after some kind of heuristic model. But you could also just write out a program like token by token. If you know that your program comes from a fixed set of tokens, you can basically just output them one by one and train an RNN to do this. And then another like strategy could be to output a vector in an embedding space and then use like nearest neighbors to find the closest program that satisfies the constraint that it's valid over the input-output examples. So these are all like different kind of potential approaches and have all been tried to various degrees. But one thing I will point out is that this is a different problem than program induction, which is a very cool idea where you can train a neural network that goes from input data directly to output data. In our case, that doesn't work because we're trying to learn a program that's reproducible and interpretable by the human. We already know what they want the output data to look like. We need to figure out the program, not just get the output data. So yeah, so robust fill was kind of the first one of the first attempts to do like neural programming by example in this way. And the way it works is that you take your input examples and you take your output examples, and you basically encode them in some like character way, feed them through LSTMs, and you output your program token by token. This is for one input-output example pair. But for multiple ones, you need something that basically can look at all the programs as they're being outputted. And the way the paper did this is with like a pooling step and a classification step afterwards. So it's generating, each examples has a program being generated token by token, but then those at every time step, that gets fed through another layer to actually predict what the most likely next token is. So this is great, but how do you make sure it's valid over the examples? Because there's not a guarantee anymore. And the way that they approach this is in the decoding step, beam search is this like common way of like getting the most likely sequence of output tokens. They modified it to also enforce this constraint that the output result is consistent, as consistent with the examples as possible. So there is a slight level of potential failure in this case, because even with like a very large beam, you still might end up with a place where the neural network just can't predict a program that's correct. But it was able to do pretty well on most of the tasks that flash fill and blink fill were. Yes, and the one thing is that the DSL in this case is the string concat-based DSL that's the same as flash fill and blink fill. So that part has stayed the same. So some good things about this, it's continuous space. So something that's really cool is that when users are like entering data, entering examples in your product, it can actually handle noise potentially much better than a lot of these deterministic methods. So typos that someone might enter in their examples might not throw off the network as much as other like methods would. And yeah, I mean, potentially could be trained on data directly. No need for any kind of like heuristics there. Some cons though. So it's hard to interpret the results. We definitely have run into this problem with like other probabilistic models where a big part of our application is interpretability, and everything that happens to people's data, we want them to be able to see and interact with and play with. With things like robust fill, it's definitely a lot harder to do that. And there's a lot of research that goes into like neural network interpretability and testing, but it's still kind of an open question. And again, it's hard to verify that this will always work. So a few trade-offs, but yeah. So another really fun thing that we've run into with other like deploying other neural networks is how do we do it in users' browsers in a way that's scalable, performant, doesn't slow down their machine too much? How do you make sure that the prediction step happens in a scalable way? So at Trifacta, the way that we've implemented all of our data operations is through an engine called Photon, which is basically a C++ in-memory thing that compiles into WebAssembly and runs on people's data in a far more performant way than like raw JavaScript would. But how would you then take something like a deployed model, let's say in TensorFlow, and run it in the same way? Yeah, where do you store the weights? So memory is always like a concern. And testing, it's a little hard to make guarantees on something that's inherently probabilistic. And one of the metrics that is very commonly used in PBE is how many examples does it take to output a correct program? And would you get any guarantee that given enough examples, you could end up with a correct program or not? And then finally, usability. So is there some way that a user could provide feedback to the operation of the system besides simply doing it on more and having the network be trained on more data? So these are all open questions. These are all things that we're like investigating, but it's definitely something that brings a lot of challenges when you're trying to integrate it into a custom application. And yeah, and so the final thing I want to talk about is like just the user interface, because this also led to a lot of like really fun questions. There hadn't been really too much work in user interfaces for PBE in the past. There's some like ad hoc tools. Excel, of course, has a pretty simple interface. For us, what we did was we started with a prototype of what the interaction model could look like. And previewability is very important in our application. So in this GIF, the way it works is that as you're typing in your output example, the program is generated and then run on the rest of your inputs. So you can see exactly what's happening to your data as you're interacting with it, which is very important. But when we moved it to our main application, we did the same kind of procedure. So this is like basically a set of inputs on the left, outputs on the right. The users entered 2 examples for extracting the field of an address, and slightly grayed out are the program's kind of attempts at figuring out what the user's trying to do. But it raised a lot of questions. So in the rest of our product, we allow things like sorting and filtering and searching. Can we do that here with some kind of toolbar? And more importantly, if we know that the user should be entering examples for a certain type of format, is that something we can prompt them to do somehow? So this like led to thoughts of clustering, perhaps, based on pattern format. And it was interesting because we were developing a feature called, we were developing an entity resolution feature at the same time, standardization. And a lot of the kind of questions that we were asking here were the same as the ones that they were asking. So yeah, some more fun stuff. Let's say our ranking model is giving weights to everything, right? Then we would be able to get the top n most likely programs, not just the top one. Should users be allowed to potentially select between them? If we're, for some reason, maybe the top one isn't exactly what they want, but it's the second highest ranked one that they're actually trying to choose, should they be able to interface with PBE somehow and select that? Should they be able to edit it is a big one. If the program especially is not very interpretable, should they be able to edit it at the same time as providing examples, or is that too much user confusion? And how do we handle when things go wrong? So a lot of questions, but a few takeaways, I guess, from what we've learned so far. So programming example is really cool. There's definitely a lot of opportunity there, and it could potentially be the way that users in the future prefer to interact with data. Maybe not everyone, but there's definitely a lot of people who know exactly what they want their data to look like. They want to be able to type it out, and assuming we can extend it beyond things like string formatting, there's a lot of opportunity for this kind of automatic synthesis. And ML and heuristics, something we've kind of learned because this is a feature where we've been trying a lot of algorithms, and one of the things we've learned is that there's definitely trade-offs in expressibility and determinism. So ML gives you a lot more power potentially, but there's always a little bit of interpretability and determinism gap, and the opposite with heuristics. And building it requires effort from a lot of different people. Yeah. So hopefully we're better than this. Yep. And that's it. So please do check out trifacta.com. You can play with this for free. It's going to be available. The programming by example stuff is going to be available in a few weeks. And if you go onto our cloud product online, you can import data from your computer and then just play around with it. It's completely free to use for the basic version of our product. And feel free to reach out if you have any more questions.
Hi there, thanks for the talk. I got the point that it doesn't scale very well if the number of possible functions is large. What about if the input is large? So let's suppose you're doing, let's say, constructing JSON or XPath expressions on, medium-sized JSON or XML documents. Would that work, or would that be intractable?
That's also another scalability issue. Yeah, thanks for bringing that up. I think that one is a little bit more dependent on the language itself. So if you have, if you're outputting JSON and you have a very nice program that's not trying to output things token by token, but in this case is operating directly on the fields, then it might be a little bit less of an issue. But for us, it definitely turned out to be a big one because if the input record is very large, we're doing a lot of regex matching across the thing to figure out what's possible. And yeah, that becomes another like scalability concern.